now, this business of causation. Just because two variables happen to be correlated, and even if they're very strongly correlated, even if they had a correlation coefficient of 1, it does not mean that one causes the other. I can't stress this enough, because this is a mistake that is made time and time again, even by researchers, but certainly in the press and the media in general. So all we're doing with correlation is seeing, is there a mathematical relationship between the variables? We are not showing whether or not there is a causal relationship. Does one cause the other? All we're saying is, if one changes, the other changes. But there might be a lot of reasons why that happens. And only one of those reasons is that one is causing the other. That is a possibility, but we don't prove that with correlation. And in fact, with causation, it's not even always as obvious as we might think. I mean, I've got a couple of cartoons here that might look silly, but they're trying to make a point. I mean, we think we know, of course, there's a correlation between the aeroplane seatbelt sign coming on and the bumpiness of the ride for the next little while. But we sort of think it's the bumpiness or the potential bumpiness that's causing the light to come on. And we're probably right about that. But this little guy, you see, he doesn't know that. He thinks the light, because which comes first? The light comes on first, and then things get a bit bumpy. That's perfectly reasonable. And in fact, that's not silly, because this does happen a lot in research. If one variable happens first, and then the other variable happens, and there's a correlation between them, we think I've seen it done. People claim they've found a causation, but we don't know that for sure. The point is that little guy doesn't quite know enough about how aeroplanes work and what pilots are doing. But that's true of us too. We're also little kids when it comes to trying to understand the universe. We don't know what's going on very much. We look at just two variables, but how many more are going on behind the scenes that affect these two? We don't know very often at all. So we need to be very, very careful of claiming that we've found causation. Here's another one. So we've got these penguins down at Antarctica, and they've noticed that there's been a huge increase in film crews in the last few years, and that's just as the temperature's going up and their homeland's starting to melt a bit. Well, of course, we think we know a lot, and we can understand, well, yes, of course, that it's the melting ice caps and the increase in temperature, it's global warming, causes the film crews to go down there. If it wasn't for the global warming, they wouldn't bother. We sort of know that, but the penguins don't have that knowledge. So they're just sitting there, and they know things are warming up a bit and their ice is disappearing a bit, and they see all these film crews coming in. Is there a causal connection? Not so sure. But I mean, those are sort of trivial examples where we are doing something. So we know the cause. But in much of the scientific studies we're doing, we actually don't know, because we're not in control of it. And we need to think of ourselves much more as this little kid in the aeroplane, or as these penguins on the ice shelf, and not as sort of God looking down knowing all. We have to be very careful of that. Or else, I like this too. Okay, well, I think that makes the point. Correlation does not imply causation. Really important. So there's a lot of warnings just in this one section about dangers of using the linear model. First is the danger of outliers, and certainly of getting rid of them, just if you don't like the look of them, if they don't quite lie on your straight line nicely, big danger. And the second is the danger of what conclusions you draw, even if you've got a beautiful straight line through your data. We may discover strong correlation. Just from our mathematical study itself, we can never say we have discovered causation. Okay, so we talked a lot about this line, but we never put it in. We need to put this line in, and there's two ways we can do it. We can put in the line of best fit by eye, or we can get the calculator or computer to do it by regression analysis. you need to be able to do it by eye, and so there's a big question here: which points have to go on this line of best fit? Well, here's an interesting point. There is only one, and it's none of the data points. If you're going to be fitting a line of best fit by eye, you have to do one more thing. Find the mean of x, mean of all the x values, if that's one of your variables. If the other variable is y, find the mean of y, plot that on your graph. So mean x and mean y, that'll be a point on your graph. That's the only point that the line of best fit has to go through. And that's a surprise to some students. Some seem to have been brought up with the idea that the line of best fit should go through as many points as possible. But that's not true. It doesn't actually have to go through any of the data points. It just has to go through the mean of them. And after that, you're just trying to basically get through the mean and then approximately as many data points above the line as below the line. It's a little bit rough, but you can do a reasonable one. A slightly more accurate or a more repeatable way of doing it is using regression analysis, which the calculators do, and we'll be able to do that using the graphic calculator too. But I don't want to go into the details of that. That's not terribly important at this stage of the course. So we're going to be doing correlation. We're going to be able to put a straight line through. We're going to either do this by eye or by regression analysis. But the important thing then is we've got our straight line. We know a lot about straight lines. We can get an equation for that straight line. Either if we're doing it by eye, we'll have to work it out ourselves, but we can do that. Or if you use the calculator, it will give you the equation of the line straight off. And it will also give you the correlation coefficient at the same time. So that's quite nice. But once we've got our straight line, then we can do wonderful things. We can go between and beyond. This means we've got our data points, but once we've done our linear modeling of the data, we can get much more information because the data points there's just a few of them. Suppose we want to find out something about the data that we don't have a point for. Well, with the equation of the straight line, it's easy. We just substitute in. But there are dangers here too. Let's just, before we look at those, just get a definition here. The word poles is quite important, not used a lot, but it does make sense if you understand its use. The poles are the two extreme points on your data set once you've graphed it on a scatter plot. So the one with the lowest x value is called the lower pole, and the one with the greatest x value is called the upper pole. And that's still true even if they have a negative gradient. So the one to the left of the diagram is the lower pole, the one to the most to the right is the upper pole. All right, so these are our poles. And now we can do interpolation and extrapolation. Well, here's the word pole. Inter, between or within, between the poles. Extra, outside, more than, outside the poles. So this makes sense. The origin of the words tells us what we're doing. Interpolation might mean, suppose we've got these points here, that one, and then the next x value is this one. Suppose we wanted to know what the value of y was for some x in between here, this x value here. We don't have any data for that. But once we have the equation of the straight line, it's easy. We just substitute this value of x in and we'll get that value of y. Or we can just read it off the graph if we've got an accurate graph drawn. This is called interpolation, getting some values between the ones we already have. Often we want to do more. We want to predict, forecast, and that's always means extrapolating, going beyond the data. Often to the right, but maybe to the left. Either of these is called extrapolation if we're trying to predict what was happening down here or what's going to be happening up here. These are extrapolation, and this is a much more dangerous thing to attempt. Interpolation is basic. If you've got a reasonable straight line with quite a reasonably high correlation coefficient, interpolation is a reasonable process to do. Extrapolation is far more dangerous, far more fraught with difficulties. Because what are we doing? We're assuming that the model carries on, and we don't have any evidence for that. Even if we've got a very good straight line in the amount of data we've got between the poles, we don't know that that's going to carry on forever, either side. It could just be a small section of the data that's linear, or just approximately linear, and it might actually be curving, and it might curve quite quickly afterwards. We have no idea. So extrapolation makes some big assumptions with little justification often. Of course, if we know our variables and we're confident that it is reasonable that they'll carry on in a linear fashion, that's okay. But if we've just got some data where we didn't know anything about their pattern, we should be very, very careful about doing any extrapolation. Let's have a look at, again, a couple of silly examples, but they make a point. So here we go. Here's a bride on her wedding day. Yesterday she had 0 husbands. Today she has 1. So we plot those points, we extrapolate, and here we go. Here's the conclusion. I'm not sure if that made her happy or not. Well, maybe that's a silly one. Look at this one though. Brian's height chart. Now this is not getting quite so silly because this is a data set of heights. They're realistic, age, and if we restricted our data to here, just put a straight line through them, it's a very strong correlation between height and age. And we could think, well, okay, let's just extrapolate. Let's find out how high he'll be at 30. And here it is. He's going to be 10 feet tall. What's that? About over 3 meters. So he'll be playing basketball. I mean, we know that's silly because we know something about the relationship between these variables. We know that things don't go on forever the way they are when we're younger. But that's my point about gathering data we don't know a lot about. Doing science, that's what research is. It's stuff we don't know much about. That's why we do research. As someone said, if we knew what was going to happen, we wouldn't be doing it. And so it's really dangerous to extrapolate from even a strong linear relationship. We don't often know what is happening up here at all. And I like this one to finish off with. Well, we can talk about Peter and whether you try his approach. Okay. So, linear modelling, it's reasonably straightforward to do it, to just put a straight line through, either by hand, by eye, and calculating the equation, or with the calculators and software that's around. So the doing of it is not hard. What's hard is making sure we're doing sensible things with it and drawing sensible conclusions.